Okay, thanks for the introduction, and I would like to thank the organizers for the invitation. Yeah, my talk is not so related to direct category, but I hope you can find something interesting in the talk. So yeah, let me start with the motivation. So actually, so one of the motivation is so-called. So there's a conjecture. So by Kawamata, so it's called Kawamata's effective non-vanishing. So here I'll just give a very simple version. So it says that if we consider X to be a projective, let me just assume it's smooth variety. Actually, smoothness is not so important. And we assume that this minus kx is nef, or just C1 is positive, some kind of positive. And we consider L to be an ample line bundle, okay? Ample line bundle or a T divisor. Then the conclusion of this conjecture is just that we have a global, non-trivial global section of L. Okay, so this L is non-trivial. Yeah, actually, this conjecture looks not so natural, right? So and also I think I asked Kawamata, but he himself doesn't believe this is true, actually. But so far there's no counterexample. Okay, so this is actually the starting point of my research. I mean, so about this talk. So just I'll give some known results about this. So for example, usually the way to show this non-vanishing is just we consider. So this is actually not right way to look at it. So actually this is just equal to the Euler characteristic of L, right? So because we have this minus k nef, and this is just Kodala vanishing, right? Kodala vanishing. So this is just Kodala vanishing. So actually, the way we look at this conjecture, I mean, currently the only way to prove this conjecture in some known case is to show this one is non-negative, and then we can use the Riemann formula, right? So the known case, one of the easiest one is when dimension of X is at most 4. Okay, so this is just by Riemann Roch plus one result is C2 is positive. Okay, C2 is positive. This is I should say this C2 is pseudo effective by Miyata. Some kind of Miyata-Yao inequality. So so even I think even the case when dimension is 5 and X is Calabi-Yau variety, this is open. So I think this is somehow quite a mysterious conjecture. Okay, and also this let's focus on the case when C1 is true. Okay, C1 is true. Then I think it is well known that by Beauville and Bogomolov, so there's a decomposition theorem that we can take an atomic cover of X to make it into 3 simpler one, right? So consists of say a billion variety and also Calabi-Yau and this hyperkähler. Okay, so let's forget about Calabi-Yau because it's quite complicated, and we don't have many tools to deal with it in algebra geometry. So today, as my title suggests, I will focus on this hyperkähler. Okay, so this let me give definition here if you don't know that. So we consider X to be a compact Kähler manifold, such that it's simply connected. Okay, and also we have this. It has a non-degenerate two form generating this space. So, and this is nowhere degenerate. Okay.
When we say that we consider the C1 equal to 0 case, is because we can reduce everything to this?
No, actually, because this looks easier. I mean, of course, you can consider another case when minus k is ample, right? So this is nap is between 0 to ample, right? So let me just say when this is one open problem is for Calabi-Yau 5-fold. So this is not known, and the other one is even when kx is ample, and this is L, then we don't know if this is non-trivial. So this is open in dimension at least I think at least 6. In dimension 5, there's I think it's solved. So even this simple case. In this simple case, we don't know. Okay, so this is two extreme cases, right? Calabi-Yau case and funnel case. But in higher dimension, we know very little. Okay. But for this case, if C1 is 0, then actually we can reduce to these three cases because taking finite cover basically does not change the non-anything of this Euler characteristic. So we can always reduce to these three cases, and abelian case is trivial because this Riemann is quite simple, right? Quite simple. So the only open case is Calabi-Yau and hyperkähler. Okay, so now let's focus on this hyperkähler. Okay, and another known result is by Long Cao and myself. So this is like 2016. We show that this is let me just short for HK. Okay, so for hyperkähler 6-fold, this conjecture is true. Okay, but the method we use in this paper is included later in my another paper by myself. So I will not explain this. Okay, so then let's focus on this hyperkähler manifold. So actually, there are only very few known examples, right? So let me just recall some known example. There are 4. So one is so-called K3 n-type. So this is a Hilbert scheme of endpoints on K3 surface, and also the other one is a Kummer type. And there are also 2 example ones. It's called Algorithm 6 and Algorithm 10. So these are Algorithm example. And the interesting is that for all known examples, this conjecture is true. Okay, so I should write maybe so this and also I should write plus their deformation. Okay. But we know that this conjecture is true for above examples. I will explain why in a minute, but so what is special for hyperkähler is that the Riemann-Roch formula becomes easy. Okay, so let me first introduce the so-called Riemann-Roch polynomial. Okay, so on hyperkähler we have a very special so-called Bogomolov-Bogomolov-Fujiki form. So consider X is a hyperkähler and the dimension is 2n. So it's always even, and we fix this the generator of the two form, and then we so the conclusion. This is the Bogomolov-Fujiki form. There is some form from X to R to R. So this is a corrective form such that if we consider any alpha here, so we consider the integration of this top intersection, then this is exactly some constant times qx to alpha to the power n. Okay, here cx is called the Fujiki constant. Okay, and also it is unique. So there's unique. So in the sense that say we have more assumption that this qx is primitive integral on this the lattice h to b. Okay, so it takes integral value on this lattice and is primitive, so it cannot be scaled. And also this qx sigma plus sigma bar is positive. Okay, so this somehow tells us how to normalize this Fujiki form. Okay, so this form is quite special. We cannot find this on Calabi-Yau varieties. Only it appears in on hyperkähler manifold. Okay, and then so a theorem due to Fujiki and later by Huybrecht says that actually this equality holds for in a more general case. So this is a theorem by Huybrecht. So it says that so if we say let me consider X is hyperkähler. So if this class beta, so we take a beta inside H4J of X, which is of Hodge type this 2J and 2J, but this is on every deformation, a small deformation of X. Every say small deformation of X. For example, here what in our mind is just when we take beta to be say the train class C2J, right? In this train class or the intersection of train class. Then we have the same formula like this. So there exists some constant depends on this beta, such that if we integral beta with alpha 2n minus 2j, then this is exactly c beta times qx of alpha to the n minus j. Okay, so this is for any alpha in H2. Okay, so Fujiki, so this inequality just we take beta to be 1 in H0, then this generalized this equality, right? No, we don't know. So it could be 0, right? So if we take beta to be 0, so we don't know this constant is positive or negative. This is the whole point, right? Because this beta, yeah, we don't have any sign on this beta. Yeah, even if we take this beta to be trend class, we don't know this is positive or negative. Yeah. Okay. But this theorem actually tells us we have a good expression of this Euler characteristic. Okay. So because we can always take this beta to be Todd class, right? So if we take beta to be Todd class, then immediately we have something some relation with this Riemann polynomial, Riemann formula, right? So this is what we call the Huybrecht Riemann formula. Okay, so especially when we take we consider a line bundle, we compute this. So this is basically just this Riemann row, right? Todd x times exclusion row. Well, yeah, here I just use the same notation as C1 of L and L. So this is just the sum of say 2i factorial and Todd 2n minus 2i x times L to the power n minus I. Okay? Sorry, it's 2i. 2i. Okay, so remember, there's no odd Chen class on hyperkähler. Okay, so everything is even. But yeah, maybe I should write integration here, and we take beta to be this guy because this guy is exactly what we have here. So then it tells us that we have some polynomial. So this I from 0 to n. So I from 0 to n, and say C of Todd 2n minus 2i over 2i factorial qx of L to the I. Okay. So we can view this as a polynomial in Q, right? So that means no matter how we take this this line bundle, as long as the cubic form they are the same, then we can compute the same polynomial, right? So we denote this by the Riemann-Roch polynomial of QXL. Okay, so this is a polynomial, and we call it the Riemann-Roch polynomial. Okay, so that means this Euler characteristic behaves very well on hyperkähler manifold. Okay? As long as we know this polynomial and we know this quadratic form, we can compute this value. Okay, and then I can answer why this known examples is true, because we know exactly what happens to this numerical polynomial for known example. Okay, so yeah, so that's right. Known. By the way, here I should note that this is a deformation environment. Okay, so that means no matter how you deform this x, the polynomial itself is the same. Okay, so in that sense, if we want to calculate all the known examples, modulo deformation, we can just pick one in each deformation family, and because maybe that one has a very nice structure, then we can compute it very strictly. Yeah, this is a good question. Actually, what I didn't mention is that this is not only a deformation environment, it's a homomorphic environment. That means, yeah, if two hyperkählers they are homomorphic as differentiable manifold, then this is constant. Yeah. Yes, only depends on the topology. Yes. So we can compute this for known examples. Yeah, actually, it turns out that although we have 4 series of examples, there are only 2 possibilities for this polynomial. Okay, so this is if it's K3n type or OG10, then this Riemann Roch of X Q is just so it's actually how say binomial number. So it's 2 over Q over 2 plus n plus 1 over n. Okay. So this is so of course in OG10 this n is 5. Okay, n is 5. And when it's Kummer type or OG6, then this Riemann Roch is just the n plus 1 times Q over 2 plus n over n. Okay, so this, yeah, actually this is not trivial. So there are actually many contributions. So let me just mention some of them. So this is in this case is by Aline San and Gosher and then. Yeah, actually, you can see that if we can compute for one ample line model, then this polynomial is okay, right? So we don't need to consider every L. We just to choose one L and we take its multiple, then we can read out this polynomial. And this Kummer type is by British and Nieper. So they are, I think they are 2 students of Huibrecht. And OG6, this is by our results. So this is by Todd and Jiang. So this is myself. But we really depend on Nieper's work. And this OG10 case is more recently. So this is by Ortiz. So the student of Witten. Okay. So
what is n for OG10?
N is half dimension. Yeah, that's fine, right? N is always a half dimension. Yes. So actually, before his computation, we guess this should be true, right? Because always the OG10 and the K3 type they have very similar structure. I mean similar topological structure. Okay. This I think this is 2011 or 2020 result. So after Ortiz compute this, then we should guess. I mean, before this, in our paper, we already guessed is that in this polynomial, every coefficient should be positive. Okay, so if this is true, then if every coefficient is positive, then of course for ample line model, this number is always positive. Then of course this number should be positive, and we are done, right? So but we are not so confirmed until we find out we know all his work. So now we can propose many conjectures because these two forms. So let me just write a conjecture, or I just write a quotation. So the first is that yeah, of course, X is hyperkähler, right? So this Riemann-Roch has positive coefficient. Okay, so we can see from these two series this is true. And the second one is that actually, so these coefficients are so-called log concave. So coefficients are log concave. That means if we consider the middle one, then it's bigger than the so the multiplication of the one next to it. Okay. So such kind of thing becomes popular because the Zhonghu's work, right? And the third one, we can conjecture more. Actually, we can conjecture that from these two examples, we know that actually the root of this Riemann-Roch polynomial, they are all negative, right? So the root of Riemann-Roch x is in R negative. Yeah, actually, if you look closer, it's not only negative, but in this set, right? So it's a even negative number. Okay. But of course, this conjecture we don't know yet, and moreover, we can guess that actually this root becomes arithmetic progression, right? So this is from -2 to minus 4 to -2 times n+1, right? So these roots are arithmetic progression. Okay, but I think this my paper is already published. So if you read the math review, actually Beauville wrote the math review, and he said this conjecture is too. I mean, the evidence is too weak, so we should not believe this conjecture. Okay. But anyway, today my goal is to tell you that this conjecture 1 is actually true. Okay? So let me just mention one word about known result. So actually this, if we consider dimension 4, so this is maybe the easiest one if you study hyperkähler manifold, right? So if you start with dimension 4, then this conjecture 1 and 2 and let me see, conjecture 1 and I think all this true. Okay, 4 is in dimension 4 is by Daniel Guan. So he because in this case the polynomial is just quadratic, right? So degree 2. So I think in this case 4 is automatic whole, and we need to study hard to show that this coefficient is positive. But anyway, he can show it. But today, I want to explain this conjecture 1 holds for any x. Okay, for any x. So as you can see from the from the expression. So this is really something about the Todd class, right? So actually it does not depend on L. So yeah, now I'm starting to analyze this problem. So this is equivalent to say that this C of Todd 2n minus 2i is positive, right? For any I. And if you take a special value of L, so this is actually not L, but so this is actually equivalent to say that we can take integration along this Todd. Yeah, let me just change the notation by this 2i. Okay, so because we are now focusing on Todd. So this Todd 2i times this sigma plus sigma bar of 2 so n minus I. So this integration is positive, right? Because we know that this one is just a C of Todd 2i times Q of sigma plus sigma bar to the n minus. Oh, sorry. Here should be 2, right? So yeah. So n minus I. Okay. So this one, yeah, this one is positive, and we want to consider this constant, and we want to show this one. Okay. So we can view this part more or less. This part should be looks like a Kähler class, right? Although it's not Kähler in X on X, but if you change the complex structure, then this one becomes Kähler, right? So we can view this one to be a Kähler class. And what we really want is that we want to show that this Todd class intersects with some Kähler class is positive. Okay. So then actually the basic idea is to say that the only thing we know about this kind of result is we need to use this Hodge-Riemann bilinear relation. Okay? So the basic idea is we use Hodge-Riemann bilinear relation. So basically, bilinear relation says that if we have something primitive, then the square of the primitive part intersect with the Kähler class is positive or negative up to the where it sits, right? Where the class is sit. But we have something, right? So then that means that somehow if so we can write Todd 2i equals to some square of something, and this is primitive, then we're done, right? But of course this is not true, but actually this is the correct direction. The correct direction is that if we want to consider this, we need to consider some kind of root of it, right? So then yeah, I think this for this case we need to consider the root of Todd. But I think yeah, you are more familiar with me than me, because it also appears in direct category, right? So we consider the Todd root of X. So this is just a power series such that the square is Todd. Okay, so this is as power series, right? So let me just denote by this to be Todd root 0 plus Todd root 2 plus, yeah, remember there's no odd one. So Todd 2n root. Okay. So but if you write this, then of course these two are, I mean, this is not the square of Todd root, right? But we have immediately yeah, let me just write here. So Todd of 2i is actually equals to Todd say root of 2k times Todd root of 2i minus 2k right? So from k from 0 to I. Okay, so this one equals to this. This is not the square we want, but actually this is a good direction. So then, so we need to solve this primitive thing, right? Because we don't know whether this Todd class they are primitive, okay? But fortunately, at the end of the day, we know that we can write down a very explicit Lefschetz decomposition for this Todd group. Okay, so yeah, I have time. So this is a theorem. Yeah, let me just write this is theorem 1. And let me explain theorem 2. Theorem 2 is Lefschetz decomposition of this Todd 2k root. Okay, so this is with respect to sigma plus sigma bar. So what it looks like, I will not write down the explicit formula, but I model some coefficient. So actually this Todd root equals to the sum of so here some primitive class I call the TPI, so TP2I. So say this wave sigma bar to the power 2k minus 2I, and this I is from 0 to the minimum of k and minus k. And here is some coefficient, okay, some coefficient. And this is the primitive part we are looking for, right? So you can view this as a wave Kähler class, right? Yeah, actually you can write a plus, but somehow it's more easier to consider it as oh sorry, here the degree is wrong, but this is not 2, okay? So you can view this the same as sigma plus sigma bar 2k minus 2I. Okay, somehow these two are equivalent, and so this is the primitive part we are looking for, and so this where this TP2I is sigma plus sigma bar primitive. Okay. So actually, if you look at this equation, then actually somehow you can solve this TP from this Todd. Actually, this one is equal to somehow is equal to a sum of this Todd 2k times sigma bar. This I minus k and k from 0 to I, something like this. So with some coefficient. Okay. So once we have this, and then we have this. But here the most interesting thing is actually what we can get is the coefficient here. So in this decomposition, this coefficient is positive. Okay, so this is something very strange, but actually it's true that this, if we find the primitive decomposition of Todd root, then it can be decomposed into some primitive part with positive coefficient. So as long as we know this is true, then actually we are done. We're done because you can just so this formula is very explicit, okay? So So as long as we know this decomposition, then we compute this Todd 2I times sigma plus sigma bar, this say n 2n minus 2I, right? So this integration. But then you can sorry, here I should mark that TP2I where it lives. So it lives in different levels. So actually this lives in H2I, 2I. Oh, sorry. So this lives in 4I, okay? So this one. So then you can see that.
Excuse me, I have a question. I'm confused about the big dot they put there. So it appears also in the decomposition of.
So these two coefficients are different. Yeah, this is just some complicated coefficient. I don't want to write down.
But they are different.
They are different. Yeah, they're different. So yeah. Yeah, let me just. Okay. Yeah, I will just write. Some circle.
Okay.
Yeah. Okay. So then this one is equal to this Todd. This I just ignore the integration. So the Todd 2k root Todd 2n minus 2k. Sorry, this is I root sigma plus sigma bar 2n minus 2I. And if we put our decomposition into here, it actually gives you some sum of some coefficient, right? So this is not the same. But some coefficient with this TP2I root TP2J times sigma plus sigma bar 2n minus 2 minus I minus J. Am I wrong? So here P means primitive. So this is something I got the notation. Okay, so 2I 2J 2. Okay, yeah, something like this. But remember, as here our decomposition, all the coefficients are positive. So here this one is also positive, right? No matter how these two, the coefficients are not the same, but if you plug everything into this formula, you get some positive coefficient with some integration, and these two are primitive. Okay, and then immediately you get that because these two are primitive, so if I and J are not the same, so these two actually are 0. And if I and J are the same, then this becomes a primitive square times the right Kähler class, and this one is always positive. So and 0 if I not J and if I is J and if I not J. Okay, so then this is the end of the proof, right? So we had all the technical part in this decomposition, right? So now the remaining thing, remaining thing is we need to get this decomposition, right? And among all this decomposition, I mean the only thing left is actually, so if we write down an explicit TP2I, what is TP2I? Then we can get the decomposition and we can compute the coefficient. So everything is linear algebra. But the only thing left is to show this TP2I is primitive. Okay. Yeah. So I cannot write a random linear combination and say that okay, we have this decomposition and then we are done. But the point is we write some explicit linear combination of this kind of thing, and we show that it's primitive, then we get this the Lefschetz decomposition. So the only thing matters is that the TP2I we define is primitive. Okay, but to show that this is equivalent to say that if we so this is not integration but actually a class. So the class is this TP2I. So this is in 4I. So it's weight this sigma times sigma bar times 2n minus 4j plus 1. Right. So this is the definition of primitivity. Okay. So it's after weight certain power of the Kähler class. So imagine that this is our Kähler class. So it becomes 0. But this is actually so this is not equivalent. This is implied that if we are lucky that this way sigma 2n, so this is not 2n, so n minus 2j plus 1. So this is almost half of this plus 1. Right? This is 0 and TP2I sigma sigma bar n minus 2j plus 1 is 0. Right? So if we have these two are 0, then this is 0. Right? Because if you take you expand this, at least one power of sigma or sigma bar is higher than this power, because this is half of this number. Okay? But then it turns out that these two are equivalent. Okay? These two. Because this TP2I is real. Okay? So this is a real class. That means it's conjugate to itself. So then we only need to show this one. Okay, this one. And to show this one, actually this becomes another kind of Lefschetz operation. Remember that this wave sigma gives us this HP of omega q to HP of omega q plus 2, right? This is some kind of Lefschetz operator. Actually, we have reversed operation. So here I denote this is not my notation. Actually, it's a Hitchin notation. So this one, so is from P omega q to H P omega q minus 2. So these two operations actually it gives SL2 representation of this cohomology class. And then to show this primitive, this is actually equivalent to show that we add this operation to this TPI. So this sigma plus sigma over 4 TP2I is 0. Right? This looks cleaner, right? Because this is just one linear operation action on our class. Here we define it in this way, but I omit the coefficient. Okay. So the only thing we need to show is that after this operation, this primitive class becomes 0. But then what we really need to do is because TP2I is defined as this, right? What we really need to do is we compute this sigma over 4 Todd root of 2k, right? So if we can compute this class, then this is 0. It's simply linear algebra, right? We know how to compute this linear combination. So the only thing we need to care about is how to compute this Lefschetz operator action on this Todd root. Okay, so this is actually the what we need to do. Okay, and then this is actually done by as suggested in the title. So actually done by the so-called Rozansky-Witten theorem. Okay. So let me just tell you the answer. The answer of this computation is actually quite clear. I mean, quite it's a very clean formula. And when I started this work, I didn't expect this to be true. But let me just write down the formula. Let me just write down the formula. It's theorem 3. So, well, what is this? This sigma over 4 Todd 2I root. This becomes exactly, here should be some coefficient. Let me just write down the coefficient here. So, I'll denote lambda sigma to be, this is a number, 24n times the initial of sigma plus sigma bar over this C2. So this is integration. So this is a positive constant. We know this. And the formula is, this is exactly the next level of Todd root with sigma bar and 1 over lambda sigma. Yeah, this one. Yeah, this theorem actually tells us if we act this Lefschetz operator on this, so it becomes the lower Todd root acts by another Lefschetz operator. Okay. So let me draw a picture here. So here we have this H2I, okay, and we have H2I minus 2, 2I minus 2, and the Todd root lives here, and this Todd root lives here, right? And what we want is we act this sigma over 4, so this becomes 2I minus 2 and 2I, okay? And then it agrees with this 1 over lambda times L sigma bar. Okay, so this is the weight sigma bar action. And if you consider these two and acting by different Lefschetz operator, they agree in the middle. Actually, this is not a I mean, we have actually 3 kinds of this type. So actually, we have we can act H 2I minus 2. So this is the conjugate of this operation, and this is L sigma 1 over lambda. But yeah, this is not this is trivial because we can take conjugation on both sides, and we can see that these two agrees in this case. Actually, there's something in the middle. Something in the middle is we can consider H 2I minus 1, 2I minus 1. And this is a Euro, say, we just fix omega, so this is a real Kähler class. I mean, no, so this is a Kähler class. Then there's a Lefschetz operator here, and this is 1 over lambda, and there's a reversed Lefschetz operator, and these two, they agree in this middle. So these two things, these 3 things are actually the consequence of this one single formula. Okay, so this actually tells some very special property of this Todd root. Okay, and especially we know that there's a corollary is that you can see these 2 pieces they agree with in the middle, right? But this way, this is the Lefschetz operation. But if you consider I is smaller than n, then this is injection, right? So this actually is injection. That means every Todd root is covered by the middle one. So I should say, so the Todd root of this, I should, in the middle one is 2 and 2, right? So it should be n over 2. Okay, so some run down. Okay. So this one determines means all Todd root. Okay, because we can just act this to read out every other Todd root. Okay, so in the middle it contains the most, all the information of all the Todd roots. This is something very special for hyperkähler. Okay, then in the, I don't have time, so what I want to, I didn't mention anything about the Rozansky-Witten series, so in the remaining 5 minutes, let me just briefly explain what happens here. So in general, you can see that this computation should be very complicated, right? Because even we don't know what is the Todd class in hyperkähler, and we don't know. I mean, this operation is quite complicated. We can write it down locally, but if you compute locally, these two, it's quite hard, right? But fortunately, there's a so-called Rozansky-Witten theory. So this is applied by Hitchin and Sawon and Nieper to deal with the cohomology of hyperkähler. And basically, the theory says that we have some. So this, I don't want to explain this bit, but we have some ring. This is a ring homomorphism. Algebra homomorphism from a space B to this cohomology ring of X, and this comes from the knot theory. Okay, and then there's so this contains the so-called Jacobi diagram. Okay, and we have some operations on the Jacobi diagram, and it reflects the cohomology class here. For example, let me just write one example. Is if we consider such kind of graph, so this is a Jacobi diagram, then it maps to the ring theory through the algebra here to be this is 6, so this is minus 12 factorial the Chen 6 of X. Okay, so that means we know very explicitly which diagram corresponds to which Chen class. Okay, and then to show this equality to be true, actually what we did is we deal with Jacobi diagram, and fortunately on here we have some very fundamental knot theory result to show that certain Jacobi diagram, the action on certain Jacobi diagram has some equality, and then we push this equality to here. We get this equality. But there's only one problem is what these two operation. We know what these two correspond to this diagram, right? But we need to compare these two operations with some very natural operation on this side. So actually, we show that these two correspond to a natural operation on the Jacobi diagram, and from the known result, we know that on the Jacobi diagram side we have equality, and then push to the cohomology side we have the equality on Todd class. I think this is the end of my talk.